CNRS&Irisa, and she's going to present Sycomore.
Thank you. So, hi everybody. So what I would like to show you today is how we can simply build a permissionless blockchain, which is based on proof of work that scale to the transaction demand. So this is a joint work with Antoine Gueulier, Romaric Ledinard, and Bruno Sericola from Irisa. Thank you. So, as you know, public blockchain are fully decentralized. There are no public key infrastructure to control the transaction, the validity of transactions, and they are permissionless, meaning that you don't have to ask for participating to the blockchain. And it turns out that with such constraints, it's impossible to solve the general consensus problem. And one of the achievements of Bitcoin and the Bitcoin-like blockchain is to rely on relational behavior and incentive mechanism to reach a consensus on the cryptocurrency state. So, as has been said this morning, the state of the cryptocurrency is represented by transactions. So this is a data structure that allows to transfer currency from one user to another user. As has been said this morning, there is no inherent notion of identities in transaction or individual account with own Bitcoins. And the thing is that ownership simply means knowing a private key which is able to make a signature that redeems output script. So Yannick showed you this thing this morning already. Clearly, a signed transaction will guarantee that only the owner of an address or an account will be able to redeem the Bitcoins. However, digital signature do not prevent double spending attack. And ideally, to prevent double spending attack, we should store permanently all the transactions in a global log, and such that any output could be redeemed by at most one subsequent transaction. And in Bitcoin, the solution to implement this property is by having a log has a totally ordered sequence of transactions, of block of transactions. And the thing is that because Bitcoin and all these cryptocurrency-based permissionless blockchain run on a distributed system, nodes will share their transaction by sending messages through broadcast or primitives. And with respect to the network, you only have two main properties to be solved, to be respected. First, the connectivity, meaning that each connected node must eventually receive a transaction. But more importantly, you need to have a network which guarantees a low latency, meaning that the ratio between the time it takes to transmit a message from one node to another node must be very, very small with respect to the time it takes to create blocks. And this is very important for many reasons. First, it will allow to keep the probability of fork very small. And for instance, in Bitcoin, it's one fork every 1,000 blocks. And the thing is that proof of work mechanism allows this ratio to continuously hold, whatever the computational power of the system. Unfortunately, because these blockchains are a chain of blocks, we are constrained by having a very, very small number of transactions which are confirmed in average. 7 in Bitcoin, 20 in Ethereum, so this is a very, very bad result. And the reason is that all these blockchains want to totally order all the transactions. And as said Pet this morning, we don't need to totally order transaction. What we just need to do is to guarantee causality between transactions. And so partial ordering of the block is sufficient. And as you will see, it will radically improve the performance of this kind of blockchains. So what I would like to show you is the fact that Sycomore, what we have proposed, will be able to improve the properties of proof of work or permissionless blockchain with the following properties. First, what we would like is a ledger that is able to have several parallel chains, not conflicting one, but several parallel chains. And this should be achieved assuming that causality between transactions is respected, of course. And a very, very simple way to do that, and not to take this parallel chain effective, is to guarantee that transaction should be partitioned over the chain, not to have a transaction that belongs to several chains, as done in Spectre, for instance. And a very simple way to partition transactions over different chains is just by partitioning them according to their identifier. So assume that here you have this Bitcoin blockchain, and what we would like is a ledger such that when the number of transactions in a block exceeds some ratio, we would like that the following blocks dynamically are constructed such that transactions which are prefixed by 0 are in the upper chain, while transactions prefixed with 1 are in the bottom chain. And if the transaction demand continuously increases, this chain should dynamically split into several chains such that all the transactions are partitioned over all these chains. So this is a very simple way, and it's make this parallelism effective in the sense that you cannot have one transaction that belongs to different chains. And it's very important to prevent double spending attack. Okay, so this is the first property we would like to. The second property would be to take advantage of the fact that we have parallel chains. And this means that what we would like is that blocks can be mined in parallel. If you have a single block which is mined every, 10 minutes, you won't take advantage of the fact that you have several chains. So what we would like is to have some capability for the ledger to authorize parallel blocks to be mined without augmenting the probability of fork, of course. These are not fork, these are split due to this transaction demand. Of course, what we would like is that miners shouldn't be able to predict the chain to which their block will be attached. This is very important because if we do not respect this property, it means that a miner will be able to devote all its computational power to a single branch, and so the system is no more resilient to 50% like in Bitcoin. So what we need to guarantee is that when miners want to create their block, they cannot predict before creating their block, during the creation of their block, to which branch they will attach their block. This is very important to maintain the high resiliency of the ledger. And finally, what we would like to is to have this ledger dynamically adapt to the transaction demand, meaning when you have an increase in the number of transactions, the ledger should grow automatically. And when the number of transactions decrease in different period of the year, for instance, this graph should dynamically shrink and perhaps giving rise to a chain of transaction if the transaction demand is very low. So we would like this happen dynamically. And of course, what we would like is that all these features should be verifiable by anyone and at any time to guarantee the security of the blockchain. Okay, so just to summarize, we would like to switch from a chain of blocks to a directed acyclic graph of blocks. So this is the ledger. We don't want to extract a chain from this graph, as done in several propositions. Okay, the model we consider is exactly the same as in Bitcoin. You have a permissionless system. The adversary doesn't own more than 50% of the computational power. Nodes have access to safe cryptocurrency, to safe cryptographic functions. And we assume that each object of the system is assumed to be uniquely identified. And of course, we do not assume PKI infrastructure. Okay, two very small definition. So we consider some parameter, Cmin, constant, which is a system constant. And we consider a chain. A chain is just a sequence of blocks such that a sequence of blocks, okay. And we say that, a sequence of blocks. We define the load of a block, which is a ratio between the number of bytes of this block divided by the maximum number of bytes authorized, for instance, 1 megabyte before SegWit. Okay, so this is a load of a block. And we say that a block, for instance, this block is splittable if the average load of the last Cmin block of the chain exceed some ratio gamma, big gamma. So we say that this block is splittable because there are too many transactions in the last blocks of the chain. Okay, and this having a block which is splittable can be verified by anyone. Anyone can see that locally you have a block, you have the last blocks of your chain are overloaded, and so this block is splittable. You have exactly the same definition for a mergeable block. A mergeable block is a block such that the last Cmin block of the chain are underloaded. So the average load of the Cmin blocks is below some parameter, small gamma. Okay, and a block which is neither splittable nor mergeable is called a regular block. So in this picture, all these blocks are regular, all these blocks are regular, and this one, those are mergeable, and this one is splittable, etc. Okay, and this property can be seen by everyone. This is important. And so here, as I said, you have this mergeable block because the number of transactions in the block is less than a given constant. I said just before, but what we would like, very important property of Sycomore is to guarantee that the predecessor of a block is not predictable nor choosable by the miner. This is very important to guarantee the resiliency of the system. So assume that I have this ledger locally, and I would like to mine my block. So what do I do? Recall that in Bitcoin header, you have some kind of commitment on the state of the blockchain, meaning that in the header of a block, you have the hash of the last block of the chain, meaning that you have a fingerprint on all the state of the blockchain. Okay. And you have also the root of the Merkle tree of the transaction that belong to the block, meaning you have some kind of fingerprint on the current state of the blockchain. The only thing we do in Sycomore to guarantee that predecessor cannot be predictable nor choosable is to augment the header of each block. What we do is that we will increase the header of the block by a set of tuples, and each tuple will consist in a commitment on the leaf block of one of the chain. So assuming that you have several chains in So these are leaf blocks, okay? And in the header of a block in Sycomore, you will have a commitment on the state of this blockchain, on the state of this one, etc., etc., etc. Exactly as in Bitcoin for one chain. And so what we do is a tuple is made of three information, a reference to the leaf block of a chain, okay? The label, I just forgot to talk about label, but this is not an issue. So initially, the chain is labeled with the empty string. And when you split, each chain is labeled with the smallest prefix of the transaction in which they belong to. And so you continue to label, and each block of the chain will inherit the label of the first block of the chain. Okay? And so when you merge, you will take the largest common prefix of the label from which you merge. Okay? That's it. So this is a label. So each leaf is associated to a label. Okay? And so in the header, what you will have, in addition to this reference to each to the leaf block, you will have the label of the successor of the leaf block, which can be exactly the same if the leaf block is regular. For instance, assume you don't have this. If the leaf block is regular, the next block will have exactly the same label. But if the leaf block is a splittable block, you will here have a label which will be 110 and here 111. This is a future subsequent label. Okay? And here, the last information is the Merkle root of all the set of pending transactions whose identifier is prefixed by the label of the successor of the leaf block. Okay, so this is the header of the block. Just to remember you, a Merkle tree is just a tree which just that each node is a cryptographic union of the children. Okay. And so you have this Sycomore, and you will have this set of tuples. And now, okay, I don't know, this block could be appended to any of these leaf blocks. Okay. Now, what we need to determine is to which leaf block I will append my block. So I need to characterize the predecessor of my block. So what I do is, exactly as in Bitcoin, I will compute the proof of work of the header, which is by definition difficult. Okay? And then the predecessor of my block will be the leaf block, which is closer to the label one of the leaf block label, and the proof of work modulo 2 to the power d, and d is a number of label in the graph. Okay? The point is that this computation is not predictable by the miner because it is derived from a proof of work, and the proof of work cannot be determined. Okay? And so when a miner will compute his proof of work, he doesn't know to which leaf block his block will be appended. And he cannot manipulate, by definition, of the proof of work. And so the predecessor is determined once the proof of work has been computed. And so there is an example. So this is the set of tuples. You compute the proof of work on the full header of the block, and then you will determine so these are the modulo, and you will determine the closest block to this modulo, which is actually 0, 1. Okay. And once you have computed this predecessor, you do not modify your header because the proof of work has been done, so you are not allowed to modify the proof of work, the header. And the only thing you do is that you will take the set of transactions whose identifier is prefixed by 0, 1, which is there. you have already the Merkle root, and you will just insert all the transactions in this block, so that this block will be appended to this leaf block. Nobody is capable of manipulating this choice, and it's not predictable by the miner. And that's it. This is exactly how you compute the predecessor of a block. Okay, so to summarize, deriving the predecessor of a block requires to solve a notoriously difficult problem. The predecessor is sealed in the block header, and you do not have any explicit reference to the predecessor in the block header. You just, as a miner, you will derive the predecessor thanks to the proof of work, which is quite simple, just one operation. And this is verifiable at any time by anyone. Okay, so this is another good thing about Sycomore is that, of course, some fork may occur, but as you will see, the probability of fork is divided by the number of branches. So the more you have branches, the less the probability of fork is. And this is quite a good result. And another one is that forks are very simple to resolve. It's exactly the same rule as in Bitcoin, meaning you will get as a graph the one whose path of confirmation is the longest. I do not have time to detail, but I can answer the question. And so, as I told you, we can modelize this creation process. And what you see is that if so what we have done is we have plotted the probability of fork according to the time. We took 30 seconds because it has been shown that in 30 seconds it's sufficient to propagate one message in the full network. Okay, and what we see is that in Bitcoin, this is this curve. You have one fork every 1,000 blocks. Okay, in Sycomore, this probability of fork will decrease with the number of chain, which is pretty nice. And for instance, if you have 20 chain, then the probability of fork is 1 over 1 million, which is pretty good. And so if you have 30 chain, for instance, then blocks can be mined every 10 seconds, 20 seconds. The point is that this is adaptive, of course. What is interesting is that you do not have any more contention to have your transaction in a block, which is pretty nice. So fees do not have to increase, which will be the case in Bitcoin, because the more you have transaction, the more numerous you will have blocks which are mined in parallel. So to conclude, I have presented the new way to organize both transaction and block in a distributed ledger. This new ledger allows to keep all the remarkable security properties of Bitcoin, and will enjoy higher throughput and self-adapt to transaction demand. We are currently implementing Sycomore. And what's next? Antoine Durand will show you a solution we propose to switch from a proof of work to a proof of stake, meaning that we could implement Sycomore in a proof of stake setting, which I hope would be good. Okay, thank you.
So if I try to do a double spending attack with different labels, then what happens?
You don't have any difference between Bitcoin and this kind of thing, because a transaction can only happen in one chain because they are partitioned on the system. So it's exactly as in Bitcoin. If you are capable of following the link of confirmation to see that a transaction, when you create a block, you are not allowed, your block will not be valid if you have some double spending transaction. Exactly as in Bitcoin. There is no difference. The thing is that we take advantage of the fact that transactions are commutable, so we can build a graph, a partial order on the transaction. And the thing is that these blocks in Sycomore can split and merge, and everyone can check that a block needs to merge, or the next block will be two merge block or two split block. This is observable by everyone.
Sorry. So transactions are assigned to subchain based on their hash.
Yes.
Can you perhaps emit transactions that have a certain beginning of the hash to overload a branch and cause a split? And what would be the consequence?
Yeah, an adversary could try to create transaction with a given prefix. The thing is that, so it would increase a chain with respect to another one. The thing is that because of our distance definition, block will have the probability that the block will be appended to a smaller branch is greater than the probability to be appended to the longer, because you compute a distance on the prefix on 2-bit string. And so it means that the block, even if you have at some time a branch which is a chain which is longer than all the other one, the next block will have a probability to be appended to the smaller chain, so that this balance will be fine. Okay.
The question was because of the block rewards. So if you perhaps increase the number of blocks, then you may have perhaps a better chance to win the lottery on, let's say, on a subchain, and therefore perhaps gain less but still have a certain return.
Yeah, but the point is, yeah, it's okay. But the point is that a miner doesn't know on which branch it will append his block. The predecessor is derived from the proof of work.
I'm not saying that it's target a particular branch, but the problem would be easier because there's more branches if you are kind of inflating it, trying to split.
But if you have more branches, the probability of focusing on...
of winning one, you don't know which one. So
okay.
You're getting an easier problem, which purpose could be configured as but anyways.
I'm not sure to
An
understand.
attack because you're making the problem of mining easier and therefore getting perhaps a smaller reward, but still
Yeah.
overloading the system for...
Yeah, sure. The reward will be smaller because it will depend on the number of chain.
Okay.
Yeah. A little bit like in Ethereum, where the reward is very small. But what is important is that the probability is not increased, as in Ethereum it is.
Question. To understand well, the probability of fork diminishes depending on the number of branches. Did you estimate by how much and over time, like by how much is probability lower?
It's just divided by the number of branches.
Is it a function over time or just by the number of branches?
I'm sorry, I can't hear you.
Does it diminish over time?
It depends. Actually, it really depends on the current state of the graph.
Okay.
So if at some point you have C graph, the probability with respect to Bitcoin, the probability will be decreased by C. This is based on the current state of the graph.